Okay, great. Cool, great. Yeah, so it's nice to be here. So I'm going to talk about something that's really at the different end of the scale in terms of the light that we're looking at, which is X-ray light, which is a very much smaller wavelength than the radio to submillimeter emission that Sarah was talking about for measuring, looking at this event horizon of the supermassive black holes. And so basically, what I'm talking about is something that came up. I should tell a story, actually. Michael Wise, who's there at the back there, he's listed on there because he's kind of inspired this idea, which is basically we had so about 5 years ago, ESA had a call, the European Space Agency, for new ideas for basically what they call Voyage 2050, which is ideas towards space missions and new technology for space science in the year 2050 and beyond. And I was having a burger chatting to Michael about what we could do, and he said, well, could we come up with something, what's the next thing in X-ray astronomy? And X-ray astronomy has done lots of things. It's done also what it's doing coming up with the Athena mission is to do high-resolution spectroscopy to study the spectrum of the light from all kinds of objects in X-rays. But what we hadn't done yet was very high-resolution imaging, and this came just a few months after the release of the EHT results, the very first ones. So we were kind of inspired by that, and we knew it was sort of possible, and actually possible to achieve similar results on a much smaller scale. And so we thought, well, let's try it, and then ESA actually went ahead and said, yes, we'll support this, and we'll start putting preliminary funding in maybe, but we have to discuss about the possibilities. But they basically gave us at least moral support, and that's how we started on this journey. So the moral of that is if somebody invites you to go and talk over a burger, take the opportunity. Okay, so yes, the interesting thing is this is the scale of the things we're talking about. You see here the EHT, which is this Earth-sized array of dishes, right, which obtains resolution of the order of tens of microarc seconds in scale so that you can resolve these event horizons of these supermassive black holes. And what we're talking about is actually has the same resolution. This instrument, it looks kind of ugly. This is a big box. The box is about 1 meter wide at the front, and that box with various X-ray optics inside can give you the same spatial resolution as we have with this whole array of dishes. And the key thing involved is that the light is a much, much shorter wavelength than the submillimeter light, and that allows you to actually get similar resolution with a much smaller scale telescope. Okay, pointing in the right direction, here we go. So to sort of explain the basis of this, so first of all you might say, well, we can make normal telescopes that size, right? If you don't need the whole Earth to do it, why don't you just do some normal imaging? And so I want to just explain some of the backstory for that. So if you want to make an image of something like this beautiful image of the sort of pillars of creation taken by the Hubble Space Telescope here, something very far away, the light rays coming from a particular direction in the sky are basically coming parallel to us. And the idea of forming an image, like in this case with the lens, is that you want it so that any light ray coming from the same direction, i.e. the same parallel course, will be focused to the same point. And the idea is then you can basically make a mini image, a mini version of the image that you see, except upside down, as it appears with this setup. But you can basically form a direct image, and you can make a miniature version with various magnifications and so on. So that's the idea. You put whatever detector you like here, whether it's the retina of your eye or a CCD, something on your phone or whatever. You can do sort of more complicated things with telescopes where you use reflecting optics, and you put some sort of detector sort of further with maybe some mirrors as well, so you can run the detector outside of the actual viewing region of the telescope. But it works in the same way. You basically just take light rays coming from the same direction in the sky, and they are all, no matter where they come in your telescope, as long as they're coming from the same direction, they're mapped to a fixed point at the focal point of your setup, which allows you to make an image on the detector. Okay, sounds great. And in theory, I'm giving you the first interpretation of light, which is rays of light. In theory, this should be able to give you infinitely precise images. But of course, it doesn't in practice for two reasons. The first kind of mundane reason is that the optics that we build isn't precise enough. So actually the light doesn't go to the focal point, it goes off slightly, and we get a blurry image. Okay, so that's just basically based on our technical limitations. But what I'll tell you is that actually in optical light and infrared light at the moment, we can make perfect optics actually to the limits of this. This isn't really a problem for us, right? In things like the James Webb Space Telescope, for example. Okay. The limiting case is this thing called the diffraction limit. And that arises from this other aspect of light, which is we can think of it also as waves, right? And with waves of light, if you have an aperture, which is, for example, our mirror or our lens, that imposes this effect called diffraction, seen, for example, in the case of these water waves here, where you end up getting the waves, sort of the light rays, sort of, or the waves that we can also think of in this way, they kind of curve and bend outwards, and they end up just spreading. And the same thing happens with the optical light here, in this case, that it spreads out and again makes a blurry image at the detector. And this is the fundamental limit, because this is not based on the quality of our optics. This is based on the laws of physics. This is the fact that actually light is inherently quantum mechanical in nature, as is everything, right? And so there is this intrinsic uncertainty that you get in the position, and it turns out that the amount of resolution you can get of your image basically depends on the wavelength of light, right? It's proportional to that divided by the size of the aperture, right? Your mirrors. And what that means is you can go better resolution by having a bigger aperture, or in the case of interferometry, combining lots of telescopes the size of the Earth, right? Or you can go to a smaller wavelength, right? To go to shorter wavelengths, you'll get higher resolution. Or, of course, ideally, you can do both, and then you're just off the scale. Okay, so this is the fundamental limit that we want to beat. So the way this works is that in X-ray, so what's happened historically is that all these points here with crosses and dots have basically reached their diffraction limit. And the bunch of here with a kind of grey blob around them, these are all interferometers of the kind that Sarah talked about with the Event Horizon Telescope. James Webb Space Telescope, in its two different wave bands here, is not interferometer, it's just perfect optics. From the point of view, it reaches the diffraction limit. It's as good as we can get. Also very expensive, of course, especially to fly in space. But in X-rays, we're very sad, because actually we are limited by the technical limits of our optics. And we can't make anything, because it turns out to get to the diffraction limit in X-rays, which is down here for these instruments of this scale, sort of meters, that's saying tens of micro-arc seconds, like the Event Horizon Telescope. But to get to that, you have to have kind of precision of your optics to the level of nanometers, the same size as the X-ray wavelength, which is impossible at the moment, and probably for a very long time. You can't make the curved type of X-ray optics that you need to make a focus and actually have that precision on the scale of the optics, so it doesn't work. But you can see that in principle, if you could get to the diffraction limit in X-rays, it would be amazing, because we could have telescopes of the same size as the ones we currently build, but with the same resolution as the Event Horizon Telescope because of the short wavelength. So that's the challenge. And to solve that challenge, you look at this part here and you say, well, how do they do it with interferometers? And actually, we want to use the same technique, but we're using it on these smaller scales just because we cannot build precise enough focusing optics to reach that precision. But we know that interferometry can work, because actually building flat mirrors and optics of the sort we can put in an interferometer is much easier. Okay, so here's how it works. What happens is, again, the wave nature of light comes in, and you get these sort of beams that come into the instrument, which are reflected at these shallow angles. That's how you have to reflect X-ray light. You have to do it at very shallow angles instead of much bigger angles like you can do in the optical. You have a so-called baseline, that's your aperture, right? So you want to make that as big as you can, like at least to fit in the spacecraft to start with, to get the best resolution. And then you put your detector. And at the detector, because you're merging these two beams, as long as you can precisely control these paths, which is much easier to control when you have flat mirrors than with curved mirrors, and make them close enough, separated by sort of the total path length, followed by these beams is only nanometers inside inside the telescope, then you get these interference patterns forming. That's exactly actually what happens with the Event Horizon Telescope, but it's just more visible here. You measure them directly on the detector instead of recording electrical signals like you can do in the radio. So you're actually recording them in situ. And the next cool thing is that you can see directly, this is actually a quantum mechanical effect, because they show up in the detector as little particle strikes that hit the detector but follow this wave-like pattern, because the particles are actually following the rules of quantum mechanics to decide randomly where they strike. And even cooler is the fact that this isn't two things interfering with each other. This is what we call single photon interference, and what that means is the photon coming in is actually interfering with itself, its quantum mechanical self, coming in the other mirror to form the pattern and then having a detection. So it's every version of light interpretation, rays, waves, particles, all the quantum mechanical stuff rolled into one. It's quite neat.
Have you tried not to look at that?
Yeah. Okay. Then the next thing is that if you have a tiny, tiny change in the direction, and I can't even draw it on here, it's so tiny, it's of order of, tens of microarc seconds. It's really tiny, and just to get an idea, an arc second is 1 millimeter seen from 200 meters away. That's 1 arc second, which is what currently you can do in the optical from the ground reasonably with good telescopes, right? Well, now we're going 10,000 times smaller than that. Okay, and if you do that and you move the signal a bit, what happens is you just get this change. You see here that the interference sort of fringes shift a little amount, such in a way so that you can actually resolve this scale, which is basically the same as the diffraction limit. So you reach down to the best possible limit, resolution. Now there's a catch to that, which is doing it this way with interferometry. You're only measuring the position in one direction on a certain scale in the sky. And what you have to do, you won't get into the details of it, but you build up multiple directions. You actually do that here by rotating the spacecraft instead of waiting for the Earth to rotate, which is what happens in radio interferometry. And you also sample multiple baselines by having lots of different types of separations, apertures, all in the same spacecraft. And if you combine all of that, then you can make an image. Okay. It's not science fiction because X-ray fringes have been measured in the lab before. There was an early attempt to try and do this. It didn't work out in the end. I think they were basically a bit too ambitious. But it is possible. So these are X-ray fringes reported in 2000. And we're going to do the same thing. We've got a lab in SRON that the plan is to measure these with an even larger baseline. This was 0.5 millimeter baseline, which gives you the same resolution as the Chandra X-ray telescope, which is the best telescope, a bit less than half an arc second, the best X-ray telescope that exists and likely will exist for decades, actually. And that's already with something in the lab, basically, with kind of off-the-shelf components. Okay. Now, one of the catches is that to get the fringes, you have to make the fringes are really finely separated by very small distance. It's of the order of something like, even with, you have to make the beams narrower and narrower in order to get a separation that you can actually measure it on a detector. So the type of detectors we use are what are called CMOS detectors, are the same kinds of detectors that are in your phones, in the cameras in your phones. A little bit different for X-rays, but the same technology. And with those, you can just about measure with this 30 micron separation, but you have to have the beams very narrowly pointing together. So you need to kind of actually arrange a pair of mirrors that kind of form the baseline, and then another pair that kind of combines them. And actually, because they kind of get in the way of each other, the two mirrors that combine and form this narrow beam, you actually have to kind of cut some slats in holes in one of them so that you actually form lots of little subbeams. So what you're doing is measuring many, many little interference patterns in order to be able to do this. So it's quite a complicated setup. And unlike going to the Atacama Desert to measure things in sub-millimeter, we're in a basement at SRON here in Leiden and building this lab experiment to actually do these first measurements with the sort of technology that we're going to use. Okay. Just to give you an idea, one other thing, another local nice thing, the great thing is actually a lot of this is sort of homegrown in the Netherlands. One is the optical technology. So to form all these little beams, there's a natural technology we want to use, which is actually also the mirror technology that will go on the Athena X-ray telescope towards the end of the next decade. And that's called silicon pore optics, and this is being developed at Cosine, which is in Sassenau, I think. Yeah. We're working together with them to make prototype optics suitable for the X-ray interferometers. And what you would have in the telescope is it's unlike any other telescope that even astronomers have seen, because what you're doing is you're forming, you actually have lots of these stacks of silicon pore optics with these lots of little holes in, which are sort of millimeter scale, and each one will produce a whole set of fringes like this. This is 1 millimeter scale, there's a little tiny dot on there, and we just measure so many of these, we add them all up, stack them up, and that's how we get the measurements. Okay. One of the challenges we have is how do we find the target? Now, one of the advantages of the X-ray sky is that it's very sparse. That's good because then we don't have a lot of extra noise. We can point in one direction, we can see the target, and we don't get other stuff because we don't have focusing optics. So we get what comes in, right, with some sort of limitations. So it's good that we have a sparse X-ray sky. We don't have lots of stuff. But it's also bad that we have a sparse X-ray sky, because how do we find our target? Now, can you guess, so first of all, these are all nearly all black holes, I think pretty much all of them, which is kind of cool in this image. And, oops, sorry, hang on. There was actually a little catch. One of those dots was actually the field of view of our X-ray diffraction, about 2 arcseconds. And so to find things, we have to do some clever stuff, and one of those is to use the most precise gyroscopes ever made, these things called ring laser gyroscopes, which will track to within micro-arcseconds the pointing of our spacecraft and allow us to go from one point to another super precisely. That also needs very precision control as well. So there's a lot of firsts that we have to do in order to do this. It's challenging, but we have, the ideas to do it. It also makes it very exciting. Just to show you what you can get, remember what Sarah said, that the very first time you do something like this, like with it doesn't look super impressive, it looks kind of low resolution. That's because if it was high resolution, we would have done it 20 years earlier. So this is how it looks, but this is, imagine now something like the solar corona, the X-ray emission from our sun, the very hot plasma surrounding our sun, even with an exoplanet going across it for good measure. So this is what you'd see from a star like our sun 30 light years away. And you can basically resolve those images. You can even see the hole caused by the exoplanet getting in the way. So this is what you can see. You can actually directly image the coronae of other stars. Okay, just as one example. But, this is about black holes. So this is Cygnus X1, and Sarah also mentioned the first black hole discovered. 7,000 light years away. This actually would fit inside half the orbit of Mercury, if you're wondering. You can image it. You would see the black hole is kind of at this, but sorry, those things have moved a bit, is there. It lights up in X-rays in accretion disk. It lights up the star. The accretion disk around it blocks the light from the X-rays and makes a kind of shadow like that. And you can see all of these features here, right? You can actually directly resolve this binary system, half the orbit of Mercury from 7,000 light years away. And even further away, the cool thing about the universe is it actually lenses the light for you effectively. The expansion of space means that something a parsec in size is always resolvable to us across the entire visible universe. And if something is bright enough, you can do it. And so one example is from 10 billion light years away to see a supermassive black hole. Imagine a load of gas falls in, it lights up, and then it illuminates a few years later the gas surrounding it a few light years away. That allows us to do trigonometric measurements of the space-time directly, because we measure the time delay, we know how fast light travels, we can measure the actual spatial separation on the sky, so you can do some amazing cosmological tricks with this. And finally, just to try and impress with the image, so this is in the future, once you take the brakes off, once you can do this with formation flying spacecraft, now imagine this is what you can do with 1 meter. Now imagine going to 10 kilometers, 10 kilometer separation, 200 kilometers to some detector craft, so maybe sometime towards the end of this century. And if you can run the movie, we could see something like this. So we take the Gargantua sort of image, and if you can find the simulation. Yeah, here we go. So you can see here, you can take a movie, you can see actual light, so you can see the ring, that's a whole photon ring, all this light bent around the black hole. But you can see there's various artifacts because I haven't filled out the full interferometer array yet. But you can see basically the turbulent gas going around the black hole, and you do absolutely amazing astrophysics. So this is kind of the showstopper that when I show people when I'm trying to get funding, right? So that's the story. So we've got an exciting time ahead. We're still very early steps, but it's happening right here in Leiden at SRON, and hopefully you'll hear news about that over the coming years. So thank you.
Thank you, Phil, for this really interesting talk and really nice video at the end. Does anyone have a question for Phil? No one? Yeah, yes?
Can you maybe explain about the X-ray particle interfering with itself?
Can you just repeat the question?
So the X-ray particle interfering with itself. Yeah, okay. So it's essentially the way that we can interpret this is both waves and particles, right? So in quantum physics, it's also a wave of probability. So the photon itself, until it's actually observed, detected at the detector, it's effectively one way of interpreting it is a probability wave, and effectively then that probability wave goes through both mirrors, basically both things that catch the photons, and that causes an interference pattern at the end, and the interference pattern tells you the probability that the photon, when it's detected, will appear in one of those pixels on the detector. Actually, that's how we simulate those images, using that fact. Now, if you want to interpret that, ask about whether it's many worlds interpretation, whether that's photons going through both mirrors in different parallel universes. Who knows? But you have to discuss that with quantum philosophers, really, I think.
Any other last question before we end? Yeah.
I was thinking about the way that you interfere the signals, and when you showed us the CMOS,
yeah, the detector, yeah.
And you showed us some the zoom in of the pixels of that, and then that image you were showing a 1 millimeter scale.
Yes.
But if the wavelength of X-rays is what, angstroms?
Yeah.
Then how does couldn't get my...
Yeah, so how do you see the fringes?
Yeah. Like
so the whole trick is the fact that you can basically, so the fringes themselves, so if you see that when I showed you the beams with the waves of light, as the beams get closer and closer together, where you see that they interfere, where they strengthen each other, right? That basically, that separation between those interference points constructive interference points, that gets further and further away. So it's to do with the fact that you've kind of, yes, it's true that in volume, in sort of one direction, it's indeed the wavelength of the light, but you're doing this trick of making the beam so close together that those points where they interfere become so far apart that you can see them and resolve them on the detector.